All right, everyone. Welcome to Beyond the Noise Signals, Stories, and Spicy Takes, the show where we dig into the stories of the people shaping the future of app based computing with a special focus on mobile. I'm your host, Matt Klein, co founder and CTO of Bitdrift, as well as the creator of Envoy Proxy. Each episode, we'll talk with engineers, founders, and technical leaders who've transformed the way their companies build, understand what's happening inside their systems. We'll dig into the challenges, the breakthroughs, the lessons learned, and wrap it all up with their hottest takes. So let's dive in. Today, I am thrilled to have Romain Guy, who worked on Android at Google for 18 years, almost the entire history of the Android product. As an engineer and engineering leader, worked on graphics, performance optimization, and a lot of other things. So I am super excited for this conversation. So thank you for joining.
Well, thank you for having me. I'm also excited to have that conversation. And I must say, I'm very jealous of your podcast voice. I've hosted a lot of podcasts and I do not sound like that. So.
It's all pretend. I'm a pretend podcaster.
Right. But at least, you've clearly worked at it. So maybe I should do that someday.
Yeah. Well, anyway, thanks for joining. I think where I typically start, and you've had such an awesome career, would love to just learn a little bit about how you started on mobile. What led you into it?
Yeah.
How did you get started on Android?
So I did join Android in 2007. It was still a secret project internally at Google. But interestingly, I'd done a lot of mobile work before that, mostly as a hobby because, Android was technically my first job out of school. But in the years prior, both out of interest and passion, and also because I worked as a journalist for French computing magazines for several years where I was writing articles about programming every month. So I was always on the lookout for topics to write about. So, at the tail end of the 90s, early 2000s, I learned how to do Palm Pilot development, how to write games on the Game Boy Advance, how to do J2ME, how to write Java code for Java Card or Java Rings. So I'd done a lot of random things on mobile. And it was always fascinating to be able to build things that you could carry with you in your pocket. I remember the very early 2000s, if you remember WAP, W-A-P on mobile phones. Yeah, so I was skiing with friends, and they see me take photos with my mobile phone, and I had those hooks that would automatically put the picture, upload it to my server, publish it on my blog, and they're like, what's going on? That's none of those words resonated with anyone around me. But it was really cool. So yeah, when the opportunity presented itself to work on Android, it was hard to say no. Although I gotta say, the way it happened was, that was for an internship, and there were folks on the Android team who knew me from past work, especially open source work in the Java world. And they told me, trust us, we can tell you what it is. You're going to love it. Just come over here. It's okay. And I think that was the right move.
And did you move to the US at that time, or had you lived here previously?
Yeah, good question. So I actually spent time in the US. I did an internship at Sun Microsystems to work on the JDK for a summer. And I loved it so much that, I called my school back in France. I'm like, hey, I'll be back in a year. So I stayed a full year. Then I went back to finish my last year of school, came back to the US for another internship, this time at Google. And what happened that summer, so I was working on Android. I also met my wife that summer. So at the end of the internship, Google was like, hey, would you like to stay? I'm like, sure. Android, and Emily yeah, I'll stay in California.
Yeah. I mean, so, there's obviously a lot to talk about in terms of all the different things that you worked on when you work on Android. I think the first topic that comes to mind for me is the experience of working on a pre-release product. I would love to learn about that more, especially from the context of a lot of people who are listening, they do software and that's fine. And we all know in software, there can be bugs and you can fix them. But when you're working on something like a phone, you're dealing with hardware. And I think that's so fascinating, especially for a V1 product where I would imagine you had a lot of bugs, and some of them were hardware bugs too.
I'll start not at the beginning, but I remember there were a couple of releases where basically the marching order was look guys, as long as we can boot to the launcher and take the update, we'll be fine. But obviously it's difficult. No, working on this was interesting for many reasons. One, it was working on an operating system, right? That's not something that a lot of software engineers get to do as an actual product, right? A lot of people may have tinkered with that. It was kind of eye-opening because you realize that an operating system, it's really just a very large application. There's no dark magic anywhere. Some bits, of course, are complicated, but, once you start working on it, it's it's a bit more complex because there's more processes, there's more services and so on, but nothing that ridiculous. The thing that was also really good working on Android like so early was the team was really small. I forget the exact size, but I think the team was maybe 40 people when I joined.
Oh, wow.
It's like all in, right? Like not just the engineers, but everybody.
Right.
And the folks I was working with, they had worked on the Xbox, they had worked on BOS, PalmOS, Web TV, stuff like that. So they were all like veterans who had done operating systems in the past. And so to me, fresh out of school, I'm like, I guess that's what corporate life is like. And I didn't realize back then that I was incredibly lucky. I was surrounded by like all the smart people, and you start emulating them, right? Like the way they work and the problems they solve, it's normal. I was like, I guess that's what I have to do too. So that part was really cool. I think one of the things I learned, and it took me years to realize I'd learned that, and I think it's a really good skill to have as software engineers, is knowing what shortcuts you can take and which ones you cannot take. So to your point, when you build a product that has hardware, there are bugs that you'll be able to fix later. There are bugs that you must address before you ship. But there's also the problem of building the platform where you have APIs. So there's all the APIs that you cannot change later for compatibility reasons, but there are architectural decisions that you can swap the engine while you're mid-flight. And Android has done that many times over the years, like, sometimes small changes, sometimes major changes without anyone noticing. And there's no, unfortunately, formula to that. It's just like it takes experience and expertise to realize, yeah. And I assume it's the same for you, in your own business. Like, you can't do everything perfectly, unfortunately.
I mean, from my perspective, I consider myself a pretty pragmatic person, and I'm willing to take shortcuts as long as you make the mental trade-off that you can fix them later. I mean, there's always a balancing act as engineers, for sure.
No, absolutely. And also the reality is that for long-lived products like something like Android, right? Because we're almost 20 years later, and obviously the hardware that we have today is widely different from what Android was designed for. I mean, the first phone I was working on at Google had a single CPU, 80 megahertz, something like 32 megabytes of RAM, and no GPU. So the way you write the code and the way you architect the code, I mean, to your point, you have to be pragmatic. It's like, if that's what you're going to ship with, it has to work on that. And then, 10 years later, you have a lot of developers complaining about some of the decisions you made. You're like, well, yeah, I agree.
So, I mean, it seems like, at least just from looking at what I know of your career history, you did focus a lot on the graphic side of things, also performance as well. I guess just tell us a bit more. Obviously, you were there early. I'm sure out of college, you worked on a lot of different things. How did you wind up getting more involved on the graphic presentation side of things? And what do you like about that space?
Yeah, good question. But that's something that I've always enjoyed doing. Like a lot of the open source work I was doing, before I started working was using the Swing UI toolkit on the Java platform, like building visual effects, animations, like taking the toolkit to places that most people didn't know you could take it. And, even my hobbies, I love taking photos. I mean, behind me, there's a bunch of cameras. I love taking photos. I'm always going on trips to take photos. So like, I'm just attracted to like anything that's visual. Yeah. So to me, that felt natural. And when you work on things like that, naturally, performance is part of it. Because if you want, your fancy visuals and animations to run well, and if you care about this kind of experience, you have to worry about performance. And that was kind of like mandatory again in the early days of Android, because the first VM, Dalvik, did not have a just-in-time compiler. So it was purely interpreted. Again, on slow CPUs.
I didn't know that. That is
right.
Very, very interesting. In that era, the server JDK was already doing JIT, right? I'm sure.
The server, yeah, they had been doing JIT for a long time. They already had hotspot. So the garbage collector was also like really slow. It was stop the world, like every GC was like 160 millisecond pause.
Interesting. Why did it not ship with a JIT engine? Was it for code size, for like some other reason? I mean,
I think it was simpler than that. It was, you have to ship for the project to keep on existing. It was difficult for Android at first. Like, Google was not a company that was known for building an OS, especially in the mobile phone space. Convincing hardware companies and the carriers to like trust Google with that was difficult. So there were deadlines. It was literally, for several years, it was like, hey, we have to ship this version of Android at that date, or that's it, we're done. So in many ways, Android was interesting because it was like being part of a startup with Google money. We were always kind of like fighting for our survival.
And I know that over time and years, there were lawsuits between Google and Oracle and Sun and like whatever else. And it's less talking about that, but it's more obviously at the time, JIT, Hotspot, all of those things existed for all the different architectures. So is it just that Google didn't want to license one of the existing
Oh, that's a good
compilers?
question.
Like why didn't it just use one of the existing tool chains?
So that actually don't even know, but I think, my personal take on it, purely personal take on it, was trying to own some of the key components of the system so that you're master of your own destiny. And the compromise there is, the first version didn't have a JIT. It came pretty quickly, like Android 2.0, I think that's when it was added. It was an interesting challenge to get. And I know that, the first versions of Android, like especially compared to iPhones, for instance, could suffer sometimes in comparison. But when you look back, like most of the time, the apps were running pretty well at 60 FPS. You had some garbage collection pauses, but the fact that we got that out of, a purely software-based system, no GPU for the UI, like no JIT, that's pretty cool. It's more like a C person started writing Java because we had to do that, right?
Yes. Yeah. I mean, there's code from that era where, especially on the server for people using Java, where they would be doing their own buffer allocators, to avoid like, allocations and garbage collection and those kinds of things.
And I did a lot of that kind of work myself in the UI toolkit, where avoiding allocations was a big one. So a lot of the APIs from that time, are designed to avoid allocations. There's a lot of like manual inlining of the code. There's a lot of, building ad hoc collections or manipulating arrays directly, just because even, making a call through an interface was expensive.
Yes.
So, it was a lot of developers were judging that, and I get it, but the role of someone working on the platform is like, if my code is ugly and difficult to maintain, that's my problem, so that you can go fast and not having to worry about it.
I actually don't know the history. Did OpenJDK exist at that time?
That's a good question. I'm not sure. But then the license, I forget what the license is on OpenJDK, but I believe we used some of the Apache Harmony stuff. So that was Apache 2.0, but that was more the libraries, not the VM, not the compiler.
But like as of right now, just in the current day, is the JIT and the runtime that runs on Android, is that still Android specific, or does it share code with like OpenJDK or something along those lines?
No, it's all Android specific. It's called ART for Android runtime. And it's interesting because it's a 3-mode system. So you have an interpreter, there's a JIT, and there's an ahead of time compiler. And the ahead of time compiler can work when the app gets installed, but it can also happen later when the device is for instance, when you plug in your device overnight, the system can look at the JIT traces and use that to inform you.
Okay.
And then on top of that, Android adopted something called R8. It's an offline optimizer, or at least shrinker. It's like ProGuard, right? It can obfuscate your code, but it can also do a lot of things to improve the performance by just rewriting your bytecode.
Right.
So the combination of all those things together, you can get like really nice behaviors out of it, as much as Java and Kotlin allow you to.
Well, I was going to say, so here's the first hot take portion of our podcast, or spicy question. I mean, when I think about Android, I think about the fact that it's based on Java. And speaking about my personal biases, but I have been in so many situations in my career of just dealing with the pains of garbage collection and just avoiding garbage collection. And I think on one hand, the fact that Android's based on Java is a beautiful decision because it's very easy to write applications and like it's great, right? On another hand, it's Java, right? And I would love to get your take from being there at that time on, was it just a no-brainer that Java was going to be the thing, or were there people that were like, no, it should have been C++? I mean, at that time, right? I'm just like trying to understand breakdown.
I think there were some disagreements, but the decision of going with Java, so that predates me starting, but my understanding, and I agree with that, it's like you get access to this massive ecosystem of millions of developers and more importantly, tools, right? Like the quality of the IDEs in the world of Java, back then it was, you had Eclipse and IntelliJ or NetBeans, and still to this day, that's super important when you're trying to bring up a platform from the ground up, because that's kind of a problem you don't have to worry about, right? You don't have to teach developers as much. You don't have to tell them like, hey, here's a crappy ID that we built, over the weekend. So I think that made a lot of sense. Like you just write your code and it's fine. Like the GC is not going to get in the way. But as someone who's done a lot of graphics, I've had to do a lot to like work around the garbage collector, and sometimes even more importantly, not being in control over the memory layout of the data. Especially on modern architectures where like that's how you get the best performance is by controlling like memory access and knowing that you're gonna chase pointers and there's nothing you can do about it is like incredibly frustrating. The reality is like for a lot of applications, it's not a big deal. I think what's difficult, and I'm curious if you run into the same thing, talking about performance with developers is always a challenge because you have folks, like me, who might be a bit too obsessed, and you have folks who just never want to deal with it. Because performance is in itself something that's difficult to do, it requires quite a bit of expertise. The tools, it can be impressive to look at a profiler. There's a lot of data to understand. And so some folks are kind of looking for like recipes to follow. And I think that leads to a lot of like cargo culting that especially over time can be damaging, right? Like we've done that ourselves. Like we gave tips to developers about what they should do or should not do. And then 10 years later, people are complaining, like, oh, I did a benchmark. Like, it's not true. We're like, yeah, no, it's not true anymore. It was back then. It's the thing. If we could automate that, like we would have done it.
Yeah. I mean, my personal experience over the years has always been that I think performance is something that, as you said, to do well is performance measurement to do well is incredibly time consuming. And I think most people don't give enough thought to what it means to even reliably benchmark something and all of that stuff. And I guess my personal experience, at least for the stuff that I've been working on, is having a performance mindset, if that makes sense, has been better.
Yes.
It's been a better return on investment to me than like micro benchmarking every particular thing, if that makes sense.
Well, that's what I try to tell folks as well, because, there's this damaging quote of premature optimization is the root of all evil. First of all, the quote is incomplete, but it's often used as a tool to not worry about performance at all. And I think that's the wrong way to think about it, because trying to fix performance after the fact can be incredibly difficult and sometimes near impossible without a large re-architecture or breaking your APIs. And we had this issue on Android in some areas. To your point, if you have a performance mindset, and again, if you try to apply pragmatism, you're like, where can I take a shortcut that will help performance? Where will it not matter? No, what I always tell developers is like, look, when you click on the button, not a big deal. In your drawing code, please be careful, right? Like, think about it.
Sure.
And I think the key is just to have enough knowledge and curiosity about computers and how the systems under you work to at least make informed decisions and to know why you did or didn't do something. And it can be incredibly difficult. You were saying like measuring the right way is difficult, but even when you measure the right, understanding what you measure is in itself extremely hard. A few months ago, I wrote an interesting blog post that shows that on Android, the runtime, the VM, if you will, reorders the fields of your class based on type and name. So depending on how you access the fields and depending on how they're named, it's going to change the performance profile because, the locality of your memory access is going to change. And so I have this silly example of a benchmark where by just renaming a field, the code goes like 4 times faster.
Sorry, it like alpha orders them or something?
Yeah, it alpha orders them.
Really?
I don't know. I don't know why.
Okay.
But that's what it does. And, and it's the kind of knowledge that, if you benchmark something and then you see a number go up or down and you're like, I don't understand. Like, that's where like it pays to be curious and to try to like dig deeper. But I also recognize that, you can't always do that for everything. It's time consuming, it's expensive, and you have a job to do probably shipping features.
Yeah, I mean, we're like jumping around on topics, but I mean, this type of conversation is a good example of something that gives me pause about the new world that we're entering with all of the AI coding tools. And I'm not a person that thinks that the tools are useless. They're not. Like
Yeah, no, absolutely. They're impressive.
But I've been doing a bunch of agent assisted coding lately, and I sit there and I think about, how is anyone in the future going to learn what I already know, right? Which is like what the code is supposed to look like, and I can guide the agent to do the right thing. If you're a new engineer, I guess what I'm saying is my fear is that in 10 years, we're going to have a giant deficit of people that have not learned all of the things that you're talking about and then know how to guide the tools to get the right answers, you know?
Yeah, no, we're not the only ones who have asked ourselves that, I guess. But you know, if you want to look at the glass half full, you can also think that maybe those agents will make that knowledge more readily accessible and available.
Yep.
A good example, like, you know, even myself, I was looking at the assembly generated by the JIT, for instance, to optimize Kotlin code. You know, reading assembly is really tedious and you have to look every opcode and so on. It's nice to feed it to an AI and just say like, hey, translate that into English. Sometimes it's a little silly. I remember one of the AIs just telling me like, oh, and starting from line 9, it does a bunch of math. I'm like, cool, thanks. I mean, that's what computers do. Like, it's not very helpful. But, you know, it's so maybe it will have the opposite effect to be the engineers who can go a step further and use the agents and have that knowledge and can be there to like save the day, you know, in whatever way or fashion.
Yeah. So, you know, going back to the perf side of things, I know that at least in the last 5-7 years, Android has started to bring on Rust, and there is more, you know, code that's coming into the core operating system. I guess I understand obviously that a lot of that was to replace like lower level C++ code from a security perspective, and that makes a lot of sense. But I do wonder is that sometimes there's the chance to replace some of the lower level Java code and actually make it perform better.
That's a good question. I don't think that's something that I don't remember hearing discussions about this, because you know we had reached the point, or like Android has reached the point where now the runtime is really good, and the VM, sorry, not the VM, and the hardware is also really good. There's a lot of things that, you know, where using Rust could be helpful, but I think it would not help in that many situations for apps, because most of the code in apps, you know, is not like high traffic code or performance sensitive code. And the cost again of like, you know, learning the language, changing your tooling, how do you interact with Java and Rust together? That's always the difficulty. I think one of the misses on Android, and then it could apply to Rust or C++ equally, but I feel like we should have made it easier to interrupt with native code, to maybe encourage apps in some areas where performance matters, to make it easier for them to like reach out to native. It's also a bit better now because, you know, what, 10, 15 years ago, you had to deal with like x86, 32 and 64 bits, MIPS.
Right.
And ARM32. Now it's all ARM64.
Yeah.
That's all.
Yeah. I mean, I'll be honest, it's still painful. I mean, at least from the bit drift side, as is probably well known, it's like our SDK is mostly written in Rust.
Yeah, I was pretty happy to see that actually.
And then we have, you know, bindings obviously in Kotlin and in Swift. And for obvious reasons, the Swift bindings are fairly trivial, right? Because it's basically native code to native code. The Java bindings are not trivial, both from a performance standpoint and just from a general understanding of what's going on. I'd actually love to hear from you. I mean, even from like a language perspective, it's not obvious to me like what you would change if you keep using Java, right? So it's like, have there been ideas thought about how to make the interop better?
Not really, but there's been work in the Java community, like I don't know if you've ever used JNA, for instance. JNA is kind of nice because it loads you load the library, and then you basically you automatically have the APIs that can talk to that library. Obviously, you're limited in what you can do, and the library must expose APIs that are very C-like. And of course, you don't fully control like the performance of those hops with JNI. What I found when doing JNI myself on the platform, what I think was the most productive way and the most performant way to do JNI was to only make JNI calls that would pass down from Java primitive types. All the calling Java methods, extracting data, you do that on the Java side. And the native function that you call just takes all those primitives. I include arrays in that. And that makes the JNI code a lot easier because you don't have that dance of like, you know, looking up the Java functions from the C++ side, calling back into the VM, making sure you're doing it the right way. Usually that's the part that's really painful. And when you do that, your JNI becomes this really thin glue. But you know, you have to like think about it this way ahead of time.
I think we'll probably have to consult with you about our SDK to see how we can do it better, because our SDK is the JNI layer is not trivial.
Yeah, and JNI also has this issue that it's not very well documented, even though a lot of people have used it, and it's very easy to make mistakes, especially when you manipulate arrays. Like if you're not careful, you're gonna copy the entire array, so obviously it's very expensive.
So let's talk a bit about, again, like at your time there, you worked on a lot of graphics related things, and this is not an area that I'm super familiar with. I think people would love to learn. And I know that on Android, the presentation layer has gone through different iterations,
Right.
From the original to Jetpack Compose, I think it's called. And I don't know. I mean, I find this to be a really interesting area.
So on Android, there's actually, you can think of the rendering pipeline end to end. There's three major components. You have the UI toolkit, that's your buttons and so on. That sits on top of what we call the canvas. The canvas, just like on the web, it's your 2D renderer. And then when a window is done doing its rendering, the buffer that the window rendered is handed over to the window compositor. That's called Surface Flinger on Android. And Surface Flinger will take all the windows that are visible on screen and then, composite them together. And it has multiple ways it can do that. So the original UI toolkit is what we call, Android is the worst naming. Like the web browser was called browser. Our toolkit was called toolkit. Our framework was called framework. So we call it the view system because the base class in that system is called view. So that's a system that existed when I arrived on Android. It's pretty powerful. There were some architectural issues that led to like some obnoxious problems. Like it's famous for this file called view.java that's something like 35,000 lines long now. It's mostly comments and most of it is getters and setters. But basically every time you add features to the UI toolkit, they kind of have to go in the base class for the most part. So like that thing keeps growing. And that means that every widget is pretty heavy in terms of memory. And also you can imagine maintaining that thing is pretty gnarly. So the Canvas API was backed by an open source library called Skia that Google acquired for Android. Skia is also used by Chrome, and it's also used by a ton of open source projects. Back then, so you had a view system, you had Skia, and Skia was CPU-based, so software renderer. And then the window compositor itself was always using either OpenGL or something we call the hardware composer. Basically, the hardware composer is an abstraction for the OEMs, for the phone manufacturers, and we tell them like, hey, here are all the windows. Tell us if you can render them yourself using some secret sauce you have in your hardware. If you can't, give them back to us and we'll use the GPU. So that was pretty cool. For Android 3.0, so the first tablet, we were at a point where the first tablet was a 720p display, and I was doing some benchmarking, and basically the takeaway was, if all we do is draw a full screen bitmap, nothing. So, full screen bitmap is your main copy, right?
Yep.
It's not faster than that. We couldn't do 60 FPS. So it's like
just from the time it would take to copy the bytes to
the
buffer, basically.
Not enough bandwidth. And that's before, and like that's basically your bitmap for your background, and you haven't even started doing the app. So it's like, okay, we need to do something, right? So that's when we decided that we would have to move the UI toolkit to render on the GPU. So what I did for that release, with the help of a couple other engineers in some areas like text, was rewrite the canvas, so the existing API, without changing it, and make it use the GPU instead. That was painful because I only had a few months to do it, and it's not the cleanest code I've ever written, probably the worst I've ever written. It worked well enough that we were able to ship that device. It was an opt-in, but the standard apps were opted in.
Was that, sorry, and just from a historical perspective, was that the first device that had an onboard GPU? Or
no, that's a good question. No, the first Android device that ever shipped had a GPU already, but the GPU was really used for gaming or maybe like video playback or like media apps.
Oh, I see. So like when an app would have to basically like go full screen and take over the screen.
Not necessarily full screen. We had a way for apps to use the GPU, not full screen, but the UI toolkit, like we were so busy building features that was like, hey, GPU sounds great. We'll worry about that when we have to.
Okay.
And then came Android 3.0. We were like, oh crap, now we have to.
Right.
So again, we're back to like being pragmatic, right? Well, now is the time that we can't take that shortcut anymore. We have to move to the GPU. And so for several years, so That GPU renderer was not Skia anymore. It was still using Skia a little bit to do some things, but it was like specific to Android and specific to the Android UI toolkit. And all the way to Android P, I think, so that would be in 2017 maybe, or something like that, I forget. That's when Android moved back to Skia, because Skia in the meantime had been working on their own GPU renderer. And it had reached a point where it made sense for us to stop investing in our own renderer and go back to Skia.
2D or 3D coordinates or polygons or something that then it renders from that effectively.
The way you talked a GPU, I mean, now it's a bit different nowadays with compute shaders, but effectively you have to send it triangles that you can texture. You have the concept of shaders, so you can actually write code. A shader is basically a program that runs per pixel, where you can compute the color of that pixel. So you can do like mathematical operations to figure out what the color of that pixel is. For instance, a gradient, right?
Yeah.
You said that pixel is at that point, that location on screen. I will compute the color based on what I know about the gradient. So it's interesting because when you have to turn everything into triangles,
right,
which they're not meant for that.
Yeah. Well, and I was thinking like there's that, and then I'm sure you're going to mention this, but what first comes to mind is dealing with text. Like that sounds like it's very complicated, actually.
Text is extremely complicated. Yeah, there's a number of ways it can be done on the GPU. The more modern way is to render text basically as vectors. That's the data that's actually in the font files. It's literally curves that represent each character. The GPUs we had back then were not powerful enough to do this. So the way it works more or less is you use the CPU to draw each character, each glyph into a texture, and then you generate for the text you want to have on screen, for each character, you generate two triangles, and then you make it point into that texture. Like we call that an atlas. And the difficulty there is that, when you're a UI toolkit, you don't know ahead of time what's going to be displayed on screen. So every frame, especially when you deal with like Chinese, Korean, Japanese like languages, or if the font size changes, you have to repopulate your atlas and try to use that texture as best as possible and pack all the pixels you can while going fast. And so we ended up with a pretty complex system where it's actually kind of like a pyramid of atlases. You start from one, you fall back into another one. We had one that was for emojis in colors versus like the usual text that's black and white, that kind of stuff. And yeah, most of the code in the renderer was actually to deal with text.
I mean, it again, like just from a layperson's perspective, I can kind of wrap my head around how you would take like a 3D polygon based thing and like map a 2D screen onto it with, some basic stuff. But then, yeah, the minute that you get into like text and other things on there and then like breaking out to video and other things, it sounds very cool.
Yeah. And the other interesting thing is the way you optimize for a GPU is very different than you optimize for a CPU. So when you talk to a GPU, especially back then, one of the things that's very important is to minimize what we call state change. So let's say that you want to draw text, then you want to draw an image, then you want to draw text again. The state of the GPU that you're going to use to draw text is going to be different than the one you use to draw an image. So the problem is that if you keep going back and forth, so text, image, you're going to lose a ton of performance. Basically, you create bubbles in the pipe where the GPU is not, either the CPU is too busy or the GPU is not busy. And so we had reached a point where that renderer ahead of time, we look at all the drawing commands that would go to the GPU, try to reorder everything that you are doing, trying to merge things. So we would do things like, oh, you're drawing 5 buttons in different locations on the screen. Let me create one virtual button made of those 5 buttons that I'm going to draw as one draw call, that kind of stuff. So it's a different mindset, but it's very interesting. And again, doing that without breaking the app, without changing the APIs, that's a lot of fun.
Yeah, because I mean, what I had talked about before, and again, I'm not an Android developer. I've heard people talk about like Jetpack Compose. That's at the app layer. That's way above what we're talking about right now, right?
It's way above.
You have multiple apps, whatever they're using, whatever drawing framework or UI framework. That's going down to the unified compositor drawing layer at the operating system layer. And that's what we're talking about right now.
Exactly.
Yes.
And then to your point, around, I forgot when, was it 2018? Something like that. We started working on what's now called Jetpack Compose. So, it's the same family of UI toolkit as React or Flutter. We had reached a point where the existing UI toolkit, there were a lot of bugs we couldn't really fix without breaking apps. there were a lot of optimizations we couldn't do just because of the architecture of the UI toolkit, or even just because we had optimized everything we could, but there were so many features at play that were like, you look at every line of code, it's like every line of code is optimized. There's no more I can get out of this. And, and also mostly the API not being very good. So the team was thinking like, hey, what if we started like unbundling the UI toolkit, and that way we can deliver bug fixes and we can deliver API changes to application developers by offering it as a library. And at the same time, we had a couple of folks working on this reactive thing, and the decision was made to like combine those two efforts, and that became Jetpack Compose. So Jetpack Compose still uses the Canvas API, so it's still using the same rendering system, so that hasn't changed. To your point, what has changed is like the high-level APIs, like the components and the widgets themselves.
You could have the high-level application frameworks play better, basically, like with the underlying hardware and the drawing engines and how people do things these days.
Yeah, so that's something that, we had thought about. The decision we made, so if I back up a little, before we did Jetpack Compose, we adopted Kotlin as an official programming language for the Java platform, for the Android platform. One of the very compelling things about Kotlin, besides it being a good language, is that it has full interop both ways with Java, right? You can call Java from Kotlin, Kotlin from Java. So to us, the story to developers was amazing. It's like, hey, no pressure when you want to start adopting Kotlin, you drop a Kotlin file in your app, and that's it. And we wanted to do the same thing with the new UI toolkit. So to do that, Jetpack Compose does not, it could have brought its own renderer as part of the library, which would have allowed us to do like, to your point, like to have them play better together, to have like more modern features, whatever. But by not doing that, by sharing the canvas with the view system, what you can do today is you have a screen that's full of the old UI toolkit. You can drop a single button that's Jetpack Compose. Or you can go the other way around. Maybe you have a custom widget that you wrote in the past and you don't want to rewrite it. And so that was, again, being pragmatic, right? That was a compromise. Like, okay, we're sacrificing something, but in return, we're making adoption kind of a no-brainer because you can go at your own pace. And I think that was a very good decision that we made.
Yeah. I mean, from the phone perspective, I actually don't know this. Is the biggest driver of battery usage, is it CPU, GPU, just the screen being on? I mean, and I guess the reason that I'm asking that is that we talk about performance. We talked a lot about CPU performance. We didn't talk about battery performance. And I would imagine that there is some battery stuff in here as well.
Yeah, so batteries is a number of things. The CPU can be a huge battery drain if you're using the big cores and you're running them full speed. I don't know what it's like on the latest phones, but I remember some of our phones where it's like, you're drawing like 2 watts, which is going to drain your battery like real fast. The GPU itself, same idea. What can use a lot of battery as well is using the radios to do networking. I'm reminded of that every day. Like my house is basically a Faraday cage. So if I stay home, the battery on my phone, like I cannot make it throughout the day because it's blocking the signal so much that the phone is constantly trying to talk to the...
Did you design your house to be a Faraday cage?
No, I did not. And I would love to find the person who did that. I was like, dude, what the hell? I was telling folks like, don't call me. I'm not going to get your call. So yeah, it really depends on what the app does. But, and of course, like the more silicon you light up. Like a good example is like Pokemon Go. I remember a lot of players, complaining about like, oh, my phone gets hot. I'm like, your screen is on, your GPU is running full blast, your CPU is running full blast. You have like the GPS on, the compass is on, like everything is on. So yes.
I could see that for Pokemon Go, but lately I've been playing Scrabble a lot with my wife, and it's like that thing drains the battery like crazy. And it's just like, really? Scrabble? Like, what's going on here?
That's where we go back to, some folks ignoring optimizations when I wish they wouldn't. And then she launches a simple looking 2D game, and then the fans go... And every time she asks me, I'm like, yeah, the game developers could have probably optimized that game. Because there's no reason like it should use... Yeah, and it's, but the thing is like, they ship the game and they're getting the audience, so should they have...
Well, they're incentivized to ship the game. I mean, yeah. Sure.
But the big difference between a game, and something like a UI toolkit is that games, I think pretty much every game out there, it's a continuous loop, right? Like, so they never stop. They will render every frame that the display can show unless they skip a frame. What a UI toolkit does, that it's rendering on demand. So there's a lot of logic inside the UI toolkit to not draw when there's no change to draw, right? And that way we save battery and performance. But games, most games, stuff moves on screen anyway. So like, why would you bother? Like, just draw all the time.
Rotate from vertical to landscape. I mean, this will be very obvious to you, but at the time, I remember very clearly that they had never done rotation before. And basically, what would happen is the minute they would rotate the phone, every app would rotate and like redraw itself, even if it wasn't showing on the screen. And it would take, I mean, it would take like 7 seconds, like to rotate, because like everything.
Yeah, I remember those days.
And I remember I spent a lot of time actually fixing the operating system to like not rotate the apps that weren't actually showing. And
like, I remember a bug we had on Android was if your lock screen, if you had a password, so not a PIN, but a password, it would show like an input field with like the blinking cursor so you could enter your password. Well, what happened was when you would turn the screen off, oops, we forgot to turn off the animation. So the blinking cursor would like in your pocket keep redrawing it, like twice a second. And turns out it's not good for the battery.
Amazing. So I don't know, are there any other interesting things that you worked on in your time at Google or Android that you'd like to share?
Yeah, no, a lot of stuff. I mean, the one that I loved working on that I was also really proud of, built with another engineer, a 3D rendering engine from scratch. It's called Filament. Yeah, it was very interesting because we had to learn, we were both like, he was the engineer who designed the window compositor and had worked on the rendering pipeline of Android. So we understood 2D. And now we had to do 3D. And turns out that adding a third axis makes things so much more complicated. Yeah, so the idea was actually to do not games. The problem on Android was, or we thought the problem was, if you wanted to do a bit of 3D in your app, let's say, your fintech company, you just want to show a credit card in 3D.
Right.
Either you write custom GL or Vulkan code, it's a pain in the ass, or you go use like a game engine, but those things are big, they tend to want to be full screen and so on. So the idea was to make a small engine that would be embeddable inside the apps, and I would give you like, nice APIs, state-of-the-art rendering and all that. A lot of our focus was on keeping the binary as small as possible while delivering super high performance. So we spent a lot of time like, staring at it's written in C++, so staring at the assembly code to see like what we can get rid of, making sure the compiler is generating the right instructions, doing vectorized code, and same thing on the GPU. And today, like for instance, the Android XR headsets that were announced in 2025, I think the Samsung XR is available now. They use that rendering engine. It's used in a few other apps at Google. So that was really interesting. And also trying to figure out the math, relearning math.
Yeah, I took linear algebra in college, and I think I have forgotten every possible thing from that at this point.
It was actually funny to relearn some of the stuff I learned in class because you learn it in a different way, and then it clicks, and you're like, oh, if only I had been taught math that way, I would have understood so much more easily. It was also interesting because we read like hundreds of research papers and papers from game developers and so on. At first, we were super confused, and then we realized that a lot of the papers sometimes they jump steps that they themselves, I don't think, fully understand.
Right.
So we ended up writing our own document where we're like, we're going to recite everything in our own words to make sure we understand, and also to make sure that we have a document that we know is correct as far as we know. So it's a long document, but it's pretty interesting, I think. The idea was also, going back to pragmatism, because it's mobile, we had to make approximations and take some shortcuts. And the goal of the doc was every time to explain why we made that decision, showing like, okay, I know that here I'm making an approximation and here's why. And I really like that approach.
Cool. Well, prior to wrapping up, what excites you in technology right now?
Surprisingly, I'm excited by audio stuff. I've never dabbled in audio programming, and so I keep trying to find time to like do some of that. And I don't know what I'm going to do with it, but I want to learn that field. It's something new.
Yeah, I also know nothing about that. I mean, it's I feel like has a lot changed in audio? Are there still advancements in audio? I don't even know.
Yeah, no, I'm sure. I think there's some parallels with the graphics programming in that you manipulate like pretty big chunks of data. So, performance is part of the art of audio programming. So obviously that's exciting. The other aspect, of course, it's on everybody's mind, but like, what's happening with AI. A lot of what's been done, those things are really impressive. They do amazing things, but I'm still waiting to see what can be done beyond LLMs. So, we're talking about optimizations like profiling, right? Like it's not an LLM problem. Like if I capture a trace of what's running on a device. I would love to have AIs who can look at those things, look across processes, look at, the state of the CPU or whatever, and guide me. But same thing with debugging. And I don't know, I'm curious to see if we're going to have models that are not just word-based, basically.
Yeah, I think a lot of the innovation is going to come not from the models, but from like the agent tool sets that are able to drive the models in loops, right? So it's like there might be like domain-specific debugging models or, trace analysis models or frameworks or something.
Yeah, but even that, like, I can't help but think, like, yeah, you could have an agent that tries to describe in words, to the model, like what they see in the debugger, but I feel like that sounds not like efficient.
We'll see. I mean, it's at the rate that the tools are improving, it is hard to know what will happen.
Yeah, but for instance, in the world of graphics, there's a lot of work being done with AI and ML that's obviously not LLMs. And so there are interesting things being done where there's micro neural networks that are being used as a form of data compression to replace textures or materials. And so we're talking about like really, really, really tiny networks that fit in a few lines of code in a shader. And I love that because it's like they're trying to explore like things that are specific to a problem, not like, oh, I have this big model,
Yep.
What can I throw at it? So I'm excited to see what's going to happen in that space. Hopefully stuff will happen.
Cool. I think we're at time. So thank you so much for joining. I think this
Well,
was
likewise, it was a pleasure.
Conversation. I think people are really going to enjoy it. So that's a wrap for this episode of Beyond the Noise, Signals, Stories, and Spicy Takes. Huge thanks to Romain for joining and sharing his story. If you had fun, drop us a review, tell your friends, or yell your favorite hot take into the void, and just make sure to tag us. I'm Matt Klein, and I will see you next time. Thank you.